Good morning, children. Today we will discuss about inertia tensor. Let us go with the presentation. Angular momentum and inertia tensor. Now here let us consider a rigid body, rotating rigid body, and here it is moving with the angular velocity omega about a fixed point O. Let us consider a rotating rigid body, and this body is rotating about a angular velocity with O about a fixed point O. And here we have x-axis, y-axis, and z-axis, and a particle P of mass mi, which is present in the body. It rotates about a fixed point O with position vector Ra and its velocity Vi. Now Vi is equals to omega cross Ra. And here, because here the body which is rotating about a fixed point O with angular velocity omega, here Ra is the position vector of the particle P. And here V is the velocity of the particular particle about the fixed point O. And let us assume O, X, Y, Z be the body set of axes fixed in the body. Angular velocity omega has the components we already know omega x, omega y, omega z along the xy z axis respectively, and we can write this one as omega equals to omega x I cap plus omega y j cap plus omega z k cap. Angular momentum of the particle P about the point O is given by Jp, that means particle angular momentum of the particle P is equals to Ra cross Mi into Vi. So here Mi is the mass of the particle P. Mi is the mass of particular particle P in the rotating body. Hence, angular momentum J of the entire body about the particular point O can be obtained by summing Jp for all the particles of the body. That is, here this is the angular momentum of a single particle P, Ra cross Mi Vi. Now let us consider the angular momentum for all the particles. So angular momentum for all the particles, we are leaving the suffix p. So J total angular momentum of all the particles, J is equals to sigma I equals to 1 to n Ra cross Mi Vi, which is equals to sigma I. So we can write like this. So Mi Ra cross Vi is nothing but omega cross Ra. That means here we are bringing this one Mi Ra cross Vi is nothing but omega cross Ra. So there we have used equation number 26 by using the definition of vector triple product we have. So let us consider the equation number this one 26 Vi equals to omega cross Ra, and here J is equals to sigma I Mi R dot R into omega minus Ra dot omega into Ra. That means here we are by using the vector triple product. That means A cross B cross C equals to A dot C B minus A dot B into C. That means here we will use this one A and this is P and this is C. So here A is nothing but MIRA, and here we are considering B with omega and C is RA. So by using this vector triple product, we will write this one like this. So J is equals to Mi Ra dot Ra omega minus Ra dot omega into Ra. That means we are arranging this one by using this one, this formula, vector triple product. So J is equals to sigma I Mi. So by multiplying Ra square omega minus Ra dot omega into Ra. So whose direction in general is not along the omega. So if Jx, Jy, Jz are the components of angular momentum along x, y, z axis respectively, then Jx can be written as sigma I Mi Ri square. Already we have this one here, equation 21. So here sigma I Mi R square omega x minus, we can write this R as xi omega x plus yi omega y plus zi omega z. So here Ra can be written as like this, xi omega x plus yi omega y plus zi omega z, and here Ra is nothing but here xi, or we can write Jx is equals to here, and that means here Jxyz components, these are the angular momentum along x component, y component, z component. That means here Jx, it is the angular momentum along x component, can be written as like this. and here jx is equals to omega. We will take common as omega x sigma I mi r square minus xi square. So here we have already, and here this one we will obtain by multiplying this one here. See here, already mi r square mi into r square omega x minus by multiplying this xi with this one. So xi square omega x plus xi by a omega y plus xi into z I omega I. So by multiplying and by taking as common as omega x, we'll obtain this term. Is it clear? Let us see. So by multiplying this one with xi and by taking common as omega x, we will obtain jx. So jx is equals to omega x sigma I mi r square minus xi square minus omega y by taking common as omega y sigma I mi xi yi minus omega z by taking common here sigma I mi into xi zi. So this is equation number 29a. Again, we will consider the angular momentum along the y-axis jy. Um, Same, by multiplying and taking common, we will obtain minus omega x by taking common as here sigma I mi xi yi plus omega y sigma I mi r square minus yi square minus omega z sigma I mi yi zi. Now jz is equals to by taking common as minus omega x sigma I mi xi zi minus omega y by taking common will sigma I mi yi zi plus omega z sigma I mi r square minus zi square. So these are the this is jx. So by multiplying with this, we'll obtain this one. Similarly, by considering jy, jz, we'll obtain this. So this is only we have taken for the x component. Here we are replacing here with xi component, and here this is the jx. So similarly, by considering jy and jz, we'll obtain this one. That means by here by using equation number 28, here we have considered here omega x, and for jy we'll consider here omega y and omega z for jz component. So by replacing those, we'll obtain jy jz like this. And these are 29a, 29b, 29c equations, and these equations can be written as jx is equals to ixx omega x plus ixy omega y plus ixz omega z. That means here, if we consider here, here let us see, ixx is nothing but sigma I mi r square minus xi square. By considering this equation number 29a, sigma mi r square minus x square is nothing but sigma I mi yi square plus zi square. So here we'll see here jx is equals to ixx. That means why we have considered ixx as ixx omega x plus, see here this one omega x, this is the term omega x, and here this one we have replaced with ixx. So this is the ixx. That means ixx is nothing but sigma I mi r square minus xi square. So this is ixx into omega x plus, again here we have omega y. We have omega y, this one mi xi y we will consider as I y. Here already we have, see here ixy. So here we have x term and y term. Here we have x term and y term. That's why we have taken as ixy into omega y plus, here we have x term and z term. That's why ixz into omega z. And jy is equals to, again let us consider, here we have x term and y term. So I yx into omega x plus, here we have this one mi into r square minus yi square. We can consider I y. So this term we can replace with Iyy, and here sigma I mi Ra square means yi square is nothing but sigma I xi square plus zi square. Again here we here we have y into z, that means Iyz into omega z. So this is the term. So jz here again. Here we have xz. That means we are replacing it izx into omega x plus. Here we have z into y. So izy into omega y plus. Here this term is nothing but izz. So here izz equals to sigma I mi into r square means z square, which is equals to this term is equals to sigma I mi into x square plus yi square. So here Ixy is nothing but minus sigma I mi xi into yi, which is equals to Iyx. So Ixz we are replacing from equation number 29, minus sigma I mi xij is equals to Izx. Iyz is equals to minus sigma I mi into yi into zi, which is equals to Izy. So we are replacing here. So here we have obtained Jx, Jy, Jz terms. So these are the equation number 30A, 30B, 30C. So for these we are replaced here from equation number 29A, Ixx, Iyy and all those terms. So the quantity Ixx is equals to sigma I mi yi square plus zi square, which is called moment of inertia of the body about the x-axis. Similarly, Iyy and Izz define the moments of inertia of the body about the y and z axis respectively. So the quantities we have here Ixy and Ixz and Iyz and all these which involve the sums of the products of coordinates, and these are called products of inertia. So any component of the angular momentum vector may be written as j alpha equals to sigma beta I alpha beta omega into beta. This is equation number 33. So here alpha beta, which is equals to x comma y comma z. So here any component of the angular momentum vector may be written as j alpha equals to sigma beta I alpha beta omega beta. Alpha comma beta, which is equals to x comma y comma z. So here equation 30 may be written as in the matrix notation. So if we consider equation number 30, this one. So we can write this one in matrix notation. So this is Jx, Jy, Jz, which is equals to Ixx, Ixy, Iy, Ixz. So here in the diagonal we can observe Ixx, Iyy, Izz, and remaining Ixy, Xz, Iyx, Iyz, Izx, Ixz, and here we have omega x, omega y, omega z. This is equation number 34A. Or we can write this one as this is j component in xyz direction. So here j equals to I into omega. So here total we have in the place of I we have 9 elements 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we have the 9 elements of 3 by 3 matrix may be recorded as a components of a single entity I. So we can write this one as single entity I, and this I is nothing but inertia tensor. So since Ixy equals to Iyx, etc. So here I is a symmetric tensor. I is a symmetric tensor. So if we denote x, y, z by x1, x2, x3 respectively, then general element of the inertia tensor is given by I alpha beta is equals to I beta alpha. Why? Because it is a symmetric tensor. That's why I alpha beta is equals to I beta alpha, which is equals to sigma I equals to 1 to n mi into delta alpha beta ri square minus xi alpha into xi beta. So this is the general element of the inertia tensor. If we denote xyz by x1 y1 z1, so we can write like this. So here alpha comma beta is equals to 1 comma 2 comma 3. So in equations 31 and 32, if you see in equations 31 and 32, the matrix elements are in the suitable form if the rigid body is composed of the discrete particles. So in case of a continuous body, summation sign is replaced by mass or volume integration. Thus diagonal element Ixx can be written as, that means here if we consider in the equations 31 and 32, the matrix elements are in the suitable form The rigid body is composed of the discrete particles. So if we consider the continuous body, summation sign is replaced by mass or volume integration. That means the diagonal element Ixx can be written as, that means here summation we are replacing with mass or volume integration. So here we are writing integration r square minus x square into dm. So here which is equals to integration rho of r square minus x square into dv. So here dm is nothing. If we consider dm is equals to rho into dv. Here dm is nothing but rho into dv. Why? Because m equals to mass into velocity, and here dm is equals to rho into dv. That's why we are replacing dm with rho of r, because here rho is the function of r. So here rho of integration rho of r square minus x square into dv, which is equals to integration rho of r y square plus z square into dv, where dm is the mass of the infinitesimal volume element dv, and rho of r is the mass density at r within dv. So the off diagonal element ixy is Ixy is equals to minus integration xy into dm, which is equals to minus integration, again dm is nothing but rho of r into dv. So we are replacing dm with rho of r into dv, so into xy. So in general, the matrix element I alpha b can be written as I alpha beta is equals to integration rho of r square delta into delta alpha beta minus x alpha x beta into dv. So this is equation number 37. So this is the about inertia tensor. Thank you, children.